One of our engineers, Priya.
Hello everyone, my name is Priya and I'm an engineer on the TensorFlow team. I work on Distributed TensorFlow and today I'm here to talk about how you can scale your training in TensorFlow using distribution strategy. So let us begin by asking the obvious question. Why should one care about distributed training? Training complex neural networks with large amounts of data can often take a long time. In the graph here you can see to train the ResNet-50 model on a single but powerful GPU can take up to 4 days. If you have some experience running complex models, this might sound rather familiar to you. Bringing down the training time from days to hours can significantly increase your productivity because you can try out new ideas faster. In this talk, we're going to focus on distributed training, that is, running training in parallel on multiple devices, such as CPUs, GPUs, or TPUs. With the techniques that we'll introduce in this talk, you can bring down your training time from weeks or days to hours with just a few lines of code and some powerful hardware. To achieve these goals, we're pleased to introduce the new Distribution Strategy API. It's an easy way to do distributed training. We have 3 key goals for distribution strategy. The first one is ease of use. We want users to be able to use distribution strategy with very little changes to their code. The second goal is to give you great performance out of the box. Ideally, the user shouldn't have to make a lot of configuration changes or code changes to get the maximum out of their resources. And finally, we want distribution strategy to be applicable in a variety of different situations. So whether you're using different hardware, different APIs, or different distributed training architectures. So with these goals in mind, let's see how you can use distribution strategy. In the first section, we're going to focus on how you can scale your training on multiple GPUs on a single machine. First, let's look at some code written for training ResNet-50 using the TF-Keras API that you heard all about earlier in the day. And first, we'll look at some code without any distribution. So first, we create some data sets for our input, both our training input and the validation input. And we'll use the TF data APIs for this. For the model itself, we'll use the ResNet-50 model that's prepackaged with the Keras application module. We create an optimizer for our training, and then we compile the model using this optimizer and provide a loss. Once the model is compiled, you can then begin your training by calling model.fit, and then evaluate how well your model has trained by calling model.evaluate. So given this code, how can you now run this on multiple GPUs? You only need to make a couple of changes. First, instantiate a class called mirror strategy. This is the distribution strategy for multiple GPUs. And the second change is pass this strategy call, strategy instance to the model.compile call. That's it. Those are the only 2 changes you need to make to now run this training on multiple GPUs. This API is available in TensorFlow release 1.11, and you can try it out today. Another thing to note is that in this example, we use the Keras API, but you can also use mirror strategy in a very similar way if you're using the estimator API in TensorFlow as well. With this API, you don't need to make any changes to your model or your training code or your input pipeline, and checkpoints, metrics, and summaries work seamlessly as well. So let's talk a little bit about what is mirror strategy under the hood. Mirror strategy implements a distributed training architecture called data parallelism. It uses mirrored variables and all reduce to do synchronous training. So let's unpack each of these a little bit. What is data parallelism? In data parallelism, each device runs the same model on computation, but with a different subset of the input. Each device computes loss and gradients based on the training samples that it sees, and we then combine these gradients across the different devices and update the model's parameters. The updated model is then used in the next round of computation. Mirror strategy mirrors the variables of your model on each of the available devices. So for instance, if you have a variable A in your model, it will be replicated as A0, A1, A2, and A3. And together, these 4 variables form a single conceptual variable called a mirrored variable. And we keep these components in sync by applying identical updates. A class of algorithms called allReduce can be used to keep the components of mirrored variables in sync. AllReduce is used basically to aggregate the gradients on different devices, for instance, by adding them up and making the result available on each device. It is a fused algorithm that can be very efficient and reduce the overhead of synchronization across the devices by a lot. There are a number of AllReduce algorithms available based on the communication that is available between the different devices. One common AllReduce algorithm is what is known as ring AllReduce. In ring AllReduce, each device sends a chunk of its gradients to a successor on the ring and receives another chunk from its predecessor. There are a few more such rounds of gradient exchanges, and at the end of the algorithm, each device has received a copy of the aggregated gradients. Ring AllReduce uses network bandwidth optimally because it's using both the upload and the download bandwidth at each host. We have a team at Google that is working on implementations of AllReduce for various network topologies and hardware. Some hardware vendors also supply specialized implementations of AllReduce for their hardware, for example, the NVIDIA Nickel. The bottom line is that AllReduce can be fast if you're working with multiple devices on a single machine or a small number of machines with fast network connectivity. So with the help of AllReduce and mirrored variables, mirrored strategy implements synchronous training. So in the picture here, you can see we have two devices, and our model consists of layer A and layer B, each consisting of a single variable. And you can see the variables are replicated across the different devices. Training begins, we get a subset of the input on each device and compute the loss in the forward pass. Then each device computes the gradients in the backward pass. Once the gradients are computed, the devices communicate with each other using AllReduce and aggregate the gradients and update the individual variables on each device. So in this way, the training is synchronized. The next forward pass doesn't begin until each device has received a copy of the aggregated gradients. Another optimization in AllReduce is to parallelize the computation of gradients at the lower layers in the network with transmission of gradients at the higher layers. So now that we've seen how to use mirror strategy and what is under the hood, let's see what type of performance and scaling you can expect to get when using mirror strategy. So we've used, for performance measurement, we've used the ResNet 50 model with ImageNet dataset, and this is a very popular benchmark for performance measurement. We've used the NVIDIA Tesla V100 GPUs on Google Cloud with a batch size of 128 per GPU. So in the graph here, you can see the number of GPUs on the x-axis and images per second processed during training on the y-axis. So as you can see, as we increase the number of GPUs from 1 to 2 to 4 to 8, the images per second processed almost doubles every time. In fact, we're able to achieve almost 90 to 95% scaling with mirror strategy. And this is very close to linear scaling, so this means as you're adding more GPUs, you're able to get the most out of them. These numbers were obtained by running the ResNet 50 model that's available in the official Model Garden repo, so you should check it out. Currently, it uses the estimator APIs, and we're working on Keras performance actively. Okay, so far we've talked about scaling onto multiple GPUs. In the next section, we'll quickly talk about how to use distribution strategy to scale to cloud TPUs. Cloud TPU stands for Tensor Processing Unit, and these are custom ASIC designed and built by Google for accelerating machine learning workloads. Here are some quick pictures of various generations of TPUs, and in the next talk, Saurabh will talk a lot more about TPUs. So how can you use distribution strategy to run your training on cloud TPUs? It's actually very similar to before, but instead of mirror strategy, now we'll use TPU strategy. So first, we create an instance of a TPU cluster resolver, and provided the name of your TPU resource. This basically helps it locate the cloud TPUs. And then we create an instance of TPU strategy and pass the cluster resolver to it, along with another argument called steps per run, which I'll come back to in a bit. And then the rest of it is the same. You can pass the strategy class, strategy instance to the compile call and fit and evaluate your model. So that's it. Those are the only code changes you need now to run your training on cloud TPUs. So you can see how distribution strategy makes it really easy to switch between different strategies on different hardware. This API will be available soon in TensorFlow's next release, which is 1.12. Let's quickly talk about what TPU strategy does under the hood. It's very similar to mirror strategy. It implements synchronous training architecture for data parallelism. TPU cores on a single host are connected via fast interconnects, and this allows for an efficient all-reduce across the different cores. Coming back to the steps per run argument that you saw in the previous slide, that is to amortize some of the communication overheads between the TPU host and the TPU and the coordinator. So setting this to a high value will ensure that you get the best performance out of the TPUs. And finally, we can also use TPU strategy to scale to cloud TPU pods, which is basically a collection of TPU hosts connected via a fast network. Okay, so we've covered multiple GPUs training, we've covered TPUs training. Let's talk about multiple machines. How can you use distribution strategy to scale to multiple machines? And this could be machines with just CPUs, or you could have a single or multiple GPUs on each. So far in this talk, we've been using TF-Keras API for our examples, but currently multi-worker distribution strategies only work with Estimator API, and we're actively working on Keras support as well. So in the meantime, for our examples, we'll use a trick called model to estimator, which basically allows you to go from a Keras model to an estimator. So to use this, we create our model as before in Keras, and we compile it. And then instead of calling fit and evaluate, we pass the model to a model to estimator call. And this gives you an estimator instance, which you can then use with the standard estimator APIs. In this case, we'll use the train and evaluate API to run the training and evaluation. Along with the estimator, you also pass it a train spec and an eval spec, which basically provide the input for your training and eval, as well as some other parameters like number of steps and so on. So in this way, you can continue to write your model in Keras, but do the training using estimator APIs. So given this code, how can you now run this on multiple workers? It's similar to before. First, you create an instance of a distribution strategy. In this case, we're going to use collective all-reduce strategy, which is optimized for multiple workers. If your machine has GPUs, then you can also specify the num GPUs per worker argument. And then you pass it to a run config call. Run config is something that we use to provide a lot of different configurations to estimator. Then you can pass this run config to the model to estimator call, and then the rest of it remains the same. Collective all-reduce strategy is available also starting TensorFlow release 1.11. So we've covered what changes you need to make to the code. Let's quickly look at how you can also set up your cluster to run for multiple workers. So let's say you're running your training program that you just saw on each of these workers, but how do they know about each other, and how do they know that they need to communicate with each other and coordinate the training? The answer is through tfconfig environment variable. If you've used Estimator's train and evaluate API before, you might be familiar with this. It's a JSON string, and it consists of two parts. The first part is the cluster, which specifies your entire cluster, and this part is the same across all the different workers. And the second part specifies the worker's task type and ID, and this is different on each worker. So in this way, you can run the same code on each worker, but with a different tfconfig. Distribution strategy takes care of detecting the tfconfig, understanding your cluster, and coordinating your training across the different workers. Because specifying this tfconfig manually for each worker can be tedious, we recommend using Kubernetes to bring up your cluster. And we've provided a template in the TensorFlow ecosystem repository that you can use for this purpose. In this template, the only change you need to make is set up the right number of worker replicas that you have in your cluster, and it'll take care of the rest. It has a macro which basically creates the tfconfig for each worker based on the parameters. So those are the changes that you need to make to run multi-worker training with collective all-reduce strategy. But what is collective all-reduce strategy? It's a new strategy that is optimized for multiple workers. It's very similar to mirrored strategy in that it implements synchronous distributed training, but it is optimized for multiple worker situations. It does the all-reduce during training using a new type of op called collective op. So what are collective ops? Collective op is a single op in the graph that is responsible for executing the entire all-reduce operation. and it can choose the best algorithm for all reduce based on a variety of different factors such as the hardware, network topology, tensor sizes, and so on. It can also do performance optimizations. For example, if you have a large number of small gradients, then it can fuse them together before doing the all reduce to save some network bandwidth. It is designed to have a plug-in architecture so that users in the future can plug in their own all-reduce algorithms that is tuned for their hardware. And finally, we plan to implement fault tolerance in the future in the strategy, so in case of worker failure, you can continue to run your training. Let's briefly look at some of the all-reduce architectures for multi-worker. We saw ring all-reduce before for the single machine case, and the same algorithm can be extended to multiple machine case as well. So imagine having all the GPUs across all the machines in a big ring, and the gradients will basically flow along this ring. This architecture is currently implemented in collective ops. Another possible architecture is called hierarchical all-reduce. In hierarchical all-reduce, we first reduce the gradients on each worker separately, and then run ring all-reduce across the different workers, and then finally the aggregated gradients flow back along the same paths. This algorithm is a work in progress in collective ops right now. So far we've been talking about collective all-reduce strategy, which allows you to do synchronous training on multiple workers. Parameter server is another very common distributed training architecture that you might have heard of. It's been supported in Estimator API for a while, and distribution strategy also allows you to do this type of training. It's very straightforward to use. Instead of using collective all-reduce strategy, now you can specify parameter server strategy. You can continue to use multiple GPUs per worker, and this is a new feature which was not available before. And that's it. And then, so this API is also available starting TensorFlow release 1.11 as well. And you also need to make a small change to your Kubernetes template to specify the number of parameter server replicas that you want in your cluster. Distribution strategy will take care of the rest. It will place your parameters automatically in a round-robin fashion on these parameter servers. So now you've seen multiple examples of how you can use distribution strategy to run your training on different type of hardware using different architectures as well as using different APIs. One more topic I want to talk about is what is known as standalone client mode to run your training. So basically to run training from a client such as your laptop. So the approach we've talked about so far is the traditional approach where you're running your entire training program on each worker in your cluster. One downside of this approach, however, is that if, let's say you want to make a change to your model, you have to stop the training on each worker and restart the process on each of them. So to address this, we're introducing a new mode of running multi-worker training, and we're calling this the standalone client mode. In this mode, you're simply running a standard TensorFlow server on each worker, which basically exposes a service to run TensorFlow graphs. And your training program is only running on your client, which can be your laptop, or it can be another machine in the cloud as well. And the client is responsible for running your training program, creating the graph, and then sending the graph over to each of the workers and coordinate the training. You need to make a small change to your Kubernetes template for this. You can specify the script as being the TensorFlow standard server instead of your training program. And the rest of the things like tfconfig remain the same. And as for the code, you need to make a couple of small changes as well. You can continue to create your strategy as before. It can be collective all-reduce strategy, it can be parameter server strategy. But then instead of passing it directly to the run config, now we create another config called distribute config, where you pass the strategy and also another argument called remote cluster. Remote cluster basically specify your entire cluster configuration. And it's similar to the tfconfig that you saw before, but now it's passed into the code on the client. Then you can pass the distribute config to the run config, and the rest of it remains the same. You can pass the config to model to estimator and so on. Since specifying your cluster manually can be tedious, we have provided a simple utility called a cluster resolver, and it's available in the TensorFlow ecosystem repository as well, along with the templates and so on. This API is also available in TensorFlow's latest release 1.11. All right, so wrap up, we've covered a bunch of different things. We've covered multi-GPU training using mirror strategy. We've covered TPU strategy to scale onto TPUs. And we've talked about a couple of multi-worker training architectures. And we've talked about how to use the standalone client mode to run training from your laptop. Let's talk quickly about what are some things we're working on in the future. Performance is always an ongoing goal. Currently, performance for multi-GPU with estimator is pretty good, and we're working on Keras performance as well as multi-worker performance. We're working on supporting multi-worker in Keras. We'll work on adding fault tolerance to multi-worker strategies, and finally, making all of these work smoothly in eager mode as well. So we've covered a lot of ground here. If there's 3 things that you remember from today's talk, use distribution strategy APIs to scale your training. They're easy to use and you don't need to make a lot of changes to your code. Second, it'll give you great performance out of the box. And third, you can use it in a number of different situations with different hardware, different APIs, and so on. Here are a bunch of resources with some documentation as well as a bunch of examples that we went through in the talk. Feel free to take a picture here. And that's it. Thank you.